handbook. Right, this is the value. This over here, it is from your structure analysis. Of the loaded shaft. Okay. So from here, we can write this will be J over C, right? And this will be equal to M Y squared plus by M Z squared plus by T X squared. And then the whole thing divided by tau max. So for solid shaft, I can't remember this now. Okay, for solid shaft, J is equal to I can't remember it now. Let me look into your let me look into the I think I got the table given in your quiz that has all the formulas. I'm going to your quiz now, okay? I think it was quiz 6. Right. Bear with me, okay? So we have the formula given on the table. So for polar moment of area, right, is pi over 2, right, multiplied by the radius. So this is C power 4, right? So this is for solid shaft. So the expression will be pi over 2 or pi over 2 C power 4 divided by C. So this will be equal to M Y squared plus by M Z squared plus by T X squared divided by tau max. Right? So you can cancel cube. So C is equal to 2 over pi, and then square root of my squared plus by mz squared plus by tx squared over tau max, right? And this will be power by 1/3. Okay. So with this, where C is the radius of the shaft. Okay. So tau max is the mechanical property. Okay. Which is one of the easiest to acquire now, right? As you can see. So this is your mechanical property, right? So the critical part of this is you have to get this right, right? If your moments in the y and z is wrong and your torque is wrong, okay, that's where the trouble is, okay? And I like to put down here note. So I'll call this equation number, what are we now? Can't remember now. The last one that we stopped is equation number 2. So equation number 3, right? Note equation number 3 is only valid when there is no axial loading and the shearing stress induced by the shear force is small. Okay, so as engineer, we need to know when to apply what. Okay, so this formula that I've written for you, right, that you have seen now, is only valid when there is no what? Axial loading and the shearing stress induced by the shear force is small. Then this expression, equation 3, is true. Okay, if not, you cannot use equation number 3. Okay, you have to consider your shear. Okay, or if you have axial loading, then you have to consider your axial loading. Later on, we'll do examples. Okay, not this week. We'll do examples where we have axial load, then you cannot apply this anymore. Okay, so this is only true, right, when there's no axial loading and the shear force is small. Okay, so the shearing stress is basically ignored. Right, so there's a theory behind it. The theory, believe it or not, is the easy part. Okay. So to quickly summarize what we've been doing for the past half an hour is I'm trying to drive the point to all of you that why are we looking at tau max? Why is tau max so critical? So tau max is critical is because the value of the tau max, right, has lower magnitude when compared to the yield, right? So that's why we are focusing on what? Tau max. Okay. Then after that, we had this is from Mohs circle, right? We got this from Mohs circle last week, right? Then we put in our moments and our torque, right? Then we got this expression, okay? And then we just rearrange the equation, and we get to see how the mechanical behavior of the material you select will determine the shaft diameter or shaft radius. Okay, so C, let's say, is the radius of the shaft. Okay. Okay, so as I said, that is the easy part. Okay, whether you believe it or not, that's the easy part. The difficult part is how to analyze what is your my, mz, and torque in the x direction. That's where it gets difficult. Not difficult, but it requires more analysis. Okay, so I've come up with a simple rule. Okay, that I want you to focus. Okay, regarding breaking down of forces based on direction of the rotation of the shaft. Okay, so I think you all have this figure available. Okay, I post it online. Okay, so I'm going to. Okay. So there are terms that I want you all to take note. Okay. So this is a shaft. Okay. You have 3 gears. Okay. So gear A, or you have the motor gear, and it's the driver. So the motor gear is the one providing the motion, right? And then, so we call it the driver. Okay. Then gear A is the driven. Okay. Gear B is the what? Driven. So driven is what the driver is driving. Okay. So the driver is the motor gear, the driven is gear A, gear B, and it's attached to this centerpiece over here, right? And this centerpiece over here is with what we address as the shaft. Okay. So I want you all to be clear with this diagram. Now, the confusing part is always this. That's what I'm going to teach you now. Okay, what is the confusing part? It's the analysis. Okay, let me highlight what is analysis. Now I would like to draw your attention regarding the rotation direction of the driver. Okay, I want you to draw attention to that. Okay, so now I'm going to change my view to draw. So now, let's say now we are going to look at the. I'll draw on this side so you can see better. Okay, I'm gonna view from the front. Okay. So this is my transformation, right? So this is my Y, this is my Z, and this is my rotation in the X. Okay. So I'm going to draw this entire shaft. Okay. What I'm trying to do now is to resolve the forces. Okay, resolving the forces is important because if your forces are wrong, your moment will be what? Out the toilet bowl. Okay. Okay. Unfortunately. So we have. So I'm going to sketch. So this is our. Oh no, wrong color. Sorry. So this is our shaft. Okay. So I'm going to label this. This is our shaft. Okay. Then the next circle I'm going to draw. Okay. The next circle I'm going to draw. And I need it to be bigger. 2 sizes bigger. It looks like an egg now. Okay, so this I'm going to, that I drew now. Over here, this is your gear A. So this is the driven. Okay, driven. And then we know, right? We are aware that is mesh, right, together with another gear. Okay. So this gear that I'm going to draw now, that is the driver gear. Okay. Or motor gear. Right. So this is your motor gear. The motor gear is a gear that's attached to a motor. Okay. Motor gear. So this is known as the driver. Right. So based on vectors, always remember that the torque and the rotation direction is always the same. Okay. So this is the this is the rotation of the gear. Okay, of the driver. Okay, so this is the rotation, and torque. Right? Now, on the driven gear, right? On the driven gear, it's going to rotate in a so if the one on top is going in a counterclockwise direction, right? Over here, this will rotate in a clockwise direction. right? So rotation and torque. So this is driver